Yeah. Certainly should not have already joined by phone. Should turn off my Bluetooth. Okay. Good morning, gang. So today we're going to continue talking about the chain rule. And then we're going to talk about implicit differentiation. Those are our two topics for this week. So I decided to push logarithmic differentiation to next week. That way this week's homework assignment isn't totally overwhelming. So we're just going to pick up right where we left off, working examples with the chain rule. Switched over to the dot cam here. We worked a lot of concrete examples last time. I want to do an abstract example or two, and I'll show you what I mean by that. Today is, this is. Circle. The chain rule is a rule for differentiating composite functions. Those are functions that are made by plugging one function into another, or maybe more than one chain like that. The basic idea is that if you've got something that looks like this, and you want to prime it, meaning you want to find its derivative, you differentiate the outer function, but leave the inside function alone, and then you multiply by the derivative of the inside function. Right, that's the main tool that we're playing with right now. A quick example to get you caught up. If last time you felt entirely lost, hopefully now with a little bit of time to rewatch videos and play around with examples. If I wanted to find the derivative of the sine of x squared, my outer function is the sine function. My inner function is the squaring function. So first, I would differentiate the outer function, leaving the inner function alone. The derivative of sine is cosine. So I'll start off with cos of x squared. That's differentiating the outer, leaving the inner alone. And then I would need to multiply that by the derivative of x squared. But of course, the derivative of x squared is 2x. So this is cos of x squared times 2x. Right, that's the basic idea, and we saw lots of examples last time. If you want to go back and rewatch the video from Wednesday to see if those examples feel a little bit more tractable now that you've had some time and you've had a minute to look at the homework, I recommend it. I did put one or two kind of challenging examples in your homework that are not as concrete, where rather than giving you the functions explicitly, I give you some information about the functions and then ask you to conjure the appropriate derivative at the appropriate point. So let's see if I can find an example like this. If not, I'll just do one from the homework. I thought I had one or two set aside here. Oh, that's right. I'm looking in the wrong section. There we go. So, fun, slightly abstract problems like this. Yeah, let me do this one with the table. So I'm given here a table of values. The column on the left are x values. Then the next column is f of x. The next column is g of x. And then I'm given f primed at some values and g primed at some values. So x's here run from 1, 2 to 3. I'm told that f of 1 is 3, f of 2 is 1, and f of 3 is 7. G of 1 is 2, G of 2 is 8, and G of 3 is also 2. F primed of 1 is 4, F primed of 2 is 5, F primed of 3 is 7, G primed of 1 is 6, G primed of 2 is 7, and G primed of 3 is 9. So I'm given this table, and then I'm told, or I'm asked, if h of x is the composite function f of g of x, find h primed of 1. And then in the second part, I'm told that, or asked if capital H of x is g of f of x, so composed in the other direction, find capital H primed of 1. So this is my task. And we have to work a little bit in the abstract here because of course I don't have formulas for f and g that I can just differentiate. So for part A, how would I find little h primed? I'm definitely not going to get a formula for it, but I know that h is f of g. So this is f of g of x primed. And then by the chain rule, I know how to differentiate a composite. That's f primed of g of x times g primed of x. So what I was asked for was little h primed of 1. So I just plug 1 in for x everywhere. That means this will be f primed of g of 1 times g primed of 1. And I go back to my table here. So g primed of 1, that's 6. F primed of g of 1, I don't know what that is off the top of my head, but I do know what g of 1 is. G of 1 is 2. So this is f primed of 2 times g primed of 1, which was 6. And then I look back to my table, f primed of 2. Well, here's the column for f primed. F primed of 2 is 5. So this is 5 times 6, which is 30. And of all the chain rule problems I gave you in your homework, if you're comfy, using the rule the way we did on Wednesday and the way we are in that first example here, I don't think you'll find those problems terrible. But I do suspect that some folks would have a little bit of a hard time with this more abstract one. So I wanted to do at least one example like this. But we're not done. We have to do part B. Here I want capital H primed of 1. So I need to start by coming up with capital H primed of x. Remember, capital H is the composite g of f of x. So this is the derivative of g of f of x. So again, I follow my chain rule. I'm going to differentiate the outer function, leaving the inner alone, and then I'll multiply by the derivative of the inner function. differentiating the outer, leave the inner alone, then multiply by the derivative of the inner. So that all looks like this. And then they told me I want to find specifically capital H primed of 1, so now I plug in 1. So this is G primed of F of 1 times F primed of 1. F primed of 1, according to my table here, is 4. F of 1, according to my table here, is 3. So this is G primed of 3 times, what did we say? F primed of 1 is 4 times 4. All right, so I just replace each of these by what I know them to be from the table. And then finally, G primed of 3 I can read off from my table also. G primed of 3 is 9. So this is 9 times 4, or 36. So you've got lots and lots of practice with these things in the homework. I encourage you to work all of them and work all of them somewhat quickly. You know, spend some real time on this. It's not super duper hard, but it does require some practice, and it's something that you really want to put the practice into, because everything we're going to do in the next few sections is dependent upon the chain rule. One fun thing I usually like to do for students at this stage also is to prove the quotient rule as a consequence of the product and chain rules. So another fun exercise. I won't go through the proof here because we have other things we need to talk about. But I'll show you the basics of how to do it. Remember, the quotient rule says that F over G, all primed, is G times F primed minus F times G primed over G squared. And one way to prove this is to think of F over G as F of X times G of X to the negative first power. So in this sense, I can treat F over G as a product, and then the piece on the right, G of X to the negative 1, I can differentiate that piece using the chain rule. So the derivative here and while this isn't something I would test you on, it is actually very useful. In practice, when I go to differentiate things, I don't use the quotient rule very often because it's usually faster to use this. I would differentiate the first guy, leaving the second alone. So this is going to be F primed of X times G of X to the negative 1 plus F of X times this thing all primed. So that's G of X to the negative 1 all primed. This piece I differentiate using the chain rule. And I'll get it to a place where you can just do some algebra. This is g of x to the negative 1 plus f of x times this piece right here. I would differentiate using the chain rule. My outer function is the negative first power, so I'll bring that power down and then reduce the power by 1. And then, so that's the derivative of my outer function. The derivative of the negative first power function says just bring the power down and then reduce the power by 1. So that looks like this, right? Forget the f here, forget the g inside. If I was differentiating x to the negative 1, I would get negative 1 times x to the negative 2. But my inside here is an x, it's g of x, so instead I need to also multiply by the derivative of the inside. And this is pretty much it. F of x times g of x to the negative 1, that's f primed of x over g of x, plus this is f of x times all this mess here is negative g primed of x over g of x squared. And so if you then have a common denominator, multiply this by g over g, and put these two pieces together. I'll do one more little algebra step for you. It's f primed over g minus f times g primed of x over g of x squared. If you have a common denominator and put those two fractions together, your quotient rule is the result. Right, this would be f prime times g minus f times g primed all over g of x squared. And oftentimes this is the faster way to differentiate a ratio, right, is to actually treat it as a product and chain rule thing rather than a quotient rule thing. But that is the last thing I wanted to show you from section 3.4. There's lots and lots of homework problems there for you to play with, and I encourage that you do so. The next thing we need to talk about is implicit differentiation, which is intimately tied to the chain rule. So we'll be leaving section 3.4 and entering section 3.5. Implicit differentiation is what's going to allow us to find the derivative of the logarithm function, and also inverse trig functions. So this, you remember, was the little bit that I used at the end of the last example. So just try to ignore that up there. That's already in your notes. We're going to begin section 3.5 on implicit differentiation. So remember what the word implicit means. Explicit, not meaning vulgar, but meaning given to you exactly, given to you as a thing. So I can give you an explicit formula. I can explicitly tell you what to do. It means I'm giving you precisely the thing mentioned. I'm not referring to it. I'm not, what's the way? I'm not, yeah, not referring to it, but being direct. So implicit is the opposite of that. Implicit suggests that there's something implied that you don't get directly. The thing that is implied when we work in section 3.5 is that every time you see the letter y, we implicitly understand that as a function of x. So what is implicit about implicit differentiation? Every time we see y, we implicitly understand that y depends on x. That is, y is not an independent variable, but a dependent variable depending upon x. In other words, y is always understood here to be a function of x. This is actually a big fucking deal. There's like 2 heavy-hitting theorems in analysis that talk about this. And the one that I would refer you to here is what's called the implicit function theorem, which says if you have an equation involving x and y, even if the graph of that equation doesn't satisfy the vertical line test, like think about the equation of a circle, x squared plus y squared equals 1. The circle definitely doesn't satisfy the vertical line test, right? Y there is not a function of x. But if you zoom in on any particular piece of the circle, you can assume that the word is locally, right? For that zoomed in piece, y is a function of x. So this is the kind of thing that's running in the background here. Let me say the circle, radius 1, centered at 0, 0. So the unit circle, the equation of the unit circle is x squared plus y squared equals 1. So y here is not given explicitly as a function of x, right? This is not solved for y. I know what the graph looks like. It looks like this. All right, this is my unit circle, whose equation is x squared plus y squared equals 1. And it doesn't pass the vertical line test. But if you were to zoom in and just take some little piece like this, so let me say this first. Overall, y is not a function of x. But locally, y is a function of x. By locally, I mean, look at this part. If you take just a little piece of the unit circle, that little piece still has the same equation, just with a restricted domain. And this little piece on its own does pass the vertical line test. That theorem I referenced, the implicit function theorem, says that as long as you don't have any vertical tangent lines in your window, you can do this. So you can take a little window, drop that window on your graph. As long as you don't have any vertical tangent lines anywhere within that window, the graph within that window will express y as a function of x. In other words, the graph in that window will pass the vertical line test. So you can assume that y is a function of x there. That's all good theoretical stuff, but how the hell do we use it? Well, suppose I wanted to find the equation of the tangent line to this circle at some point, right? Maybe I want to find the equation of the tangent line somewhere over here at like negative root 3 over 2 comma 1/2. Can I find the tangent here? Well, I'm going to need the derivative. But this isn't solved for y. So it's not like I can just differentiate to get dy dx. It's not like I don't have something here, a formula that I can differentiate nicely. It's got 2 variables in it. But the way we do this, you have 2 choices. First, you could solve that equation for y and differentiate the result. This isn't overwhelming, but it's not pleasant. If you solve that for y, you get y equals 1 of plus or minus the square root of 1 minus x squared. We could differentiate that using the chain rule, and it would be okay. But it's messy. And what's more, you actually have to pick the plus or the minus in front of the square root to correspond with the top or bottom half of the unit circle. It's a pain in the ass. Much less a pain in the ass would be if I had some formula or some way I could differentiate this whole equation, have a dy dx or a y prime show up, and then solve for that. And you can. So if I differentiate x squared plus y squared equals 1 implicitly with respect to, and you'll see this a lot, WRT, with respect to the variable x, that means I'm going to apply ddx to both sides. I'll do the right-hand side. ddx of 1, that's 0. What about on the left-hand side? Well, ddx of x squared, that's not hard. That's 2x. Here, actually, let me take this to another page, so I have more room. So I want to differentiate on both sides the equation x squared plus y squared equals 1. That gives me ddx of x squared plus y squared equals ddx of 1. So I apply the differential operator ddx to both sides of that equation. ddx of x squared is 2x plus ddx of y squared. Well, I can apply the chain rule here. So I'm going to think of y as my inner function, and it depends on x. And I'm going to think of the squaring function as my outer function. So I'll get 2y, but then I need to multiply by the derivative of the inner function, which is y prime. And on the right-hand side, ddx of 1, like we said before, that's 0. This is it. This is implicit differentiation. I just implicitly differentiated both sides of that equation. And while I don't get a super nice formula like y prime equals, at least not right away, I do get this implicit formula, which I can solve for y prime. So I subtract 2x over. I divide both sides by 2y. The 2's cancel. And we get that y prime is negative x over y. So the good stuff is here, right? Y squared, I differentiate like normal, pretending like this is an x. You know, I bring the power down and I reduce the power by 1, so I get 2y. But then, because I'm implicitly assuming that y is itself a function of x, I need to multiply by the derivative of the inside. The inside function here is just y, and so his derivative is y prime. And then I solve for y prime. So the slope of the tangent line to the unit circle at the point negative root 3 over 2 comma positive 1/2 is I take this formula and I plug these values in. It's y prime equals negative, so x over y. What is x? X is negative root 3 over 2. Y is positive 1/2. So that's You got two negatives here. That will make this positive overall. So we'll have root 3 over 2 times 2 over 1. You can cancel your 2's and you just get the square root of 3. So that's the slope of my tangent line coming from y prime. And here's my point. Therefore, the tangent line is, or has equation y minus 1/2 equals square root of 3 times x minus negative root 3 over 2. Right, using my point slope form of a line. And we can verify in Desmos.
Sorry, I have a quick question.
Yeah, go ahead.
At the beginning, did it say differentiate implicitly with 1?
With respect to x.
That's what that meant. Okay, cool.
Yeah, WRT stands for with respect to.
Thank you.
Sorry about that. So let's slide back over to Desmos. So here's my unit circle, x squared plus y squared equals 1. And I claim that the tangent to this, right over here at the point, I'll type in the point, negative square root 3 over 2, comma 1/2. There's my point of tangency. I claim that the tangent line there is y minus 1/2 equals square root 3 times x minus minus is plus square root 3 over 2, like that. And that looks like a tangent line to me. So the slope of this tangent line, we needed a derivative. Finding a derivative for this curve is challenging because it's not a function, because it fails the vertical line test. But we can still find slopes of tangents using implicit differentiation in this manner. And the thing that you need to get comfy with is differentiating the y squared to 2y prime. That's the idea. So you have plenty of problems in your homework that ask you to do this sort of thing. They give you some formula involving x and y, and they tell you to find y prime or find dy dx. We'll get a little bit more practice, and then one of the applications I want to show you is differentiating the inverse trig functions. Before we do that, I want to look at another graph here. So are there any questions about this calculation? Okay. So another fun curve, but it definitely does not have y as a function of x. You replace, get rid of these, and look at x cubed plus y cubed equals 6xy. So you get this kind of wonky loop thing here, right? This is called a folium. I think this one is the folium of Descartes. One of the points that's definitely on here, if you look for integer lattice points, is this guy. So I'd like to know, can I find the equation of the tangent line at this point? We can kind of see what it should look like. Right, it looks like the slope there might even be -1, but it could be a little bit bigger. It's hard to tell. It could be a little bit smaller. So if I wanted to find the equation of the tangent line to this curve, which definitely does not have y as a function of x, again, failing the vertical line test really hard, the equation not solved for y and not easy to solve for y. The last one we actually could solve for y if we wanted to, by subtracting the x squared over and taking square roots. If I tried the same thing here, if I subtracted this x cubed over to this side and took cube roots, there'd still be this y term trapped inside the cube root. So it'd be very hard for me to find a formula for that. It'd be very hard for me to solve that for y. So let me come back to my dot cam. And let's say find the equation of the tangent line to x cubed plus y cubed equals 6xy at the point 3, 3. Now I wouldn't expect you to know what that graph looks like. Be clear about that, right? That's not, if I was giving you this problem on a test or anything like that, I would give you the graph here. This is not a graph that I expect you guys to know or to be able to come up with in any easy way. It's complicated. But cooking up the derivative is something we should be able to do. So I'm going to differentiate implicitly on both sides with respect to x. So this is my solution. All right, so there's that WRT again, with respect to. In other words, I treat x as my variable, and I understand that y depends on x. At least locally, I can think of y as a function of x. If I do that, I'm going to apply the operator ddx to both sides. And now the derivative of the left-hand side isn't 0. It's actually a little bit complicated. Sorry, derivative of the right-hand side isn't 0. It's actually a little bit complicated. This over here, this is a product. So I'm going to need my product rule there, right? The x times y. And this stuff over here is going to require chain rule. The x cubed doesn't require the chain rule, but the y cubed does. So I'll do the left-hand side first. The derivative of x cubed is 3x squared plus. The derivative of y cubed taken with respect to x is 3y squared times the derivative of the inner, right? So I'm differentiating the outer function, that's the cubing function. So I bring the power down, I reduce the power by 1, and then I need to multiply by the derivative of the inner function. The inner function here is just y. So I get y primed as his derivative. It really is just the chain rule. So x cubed differentiates to 3x squared. Y cubed differentiates to 3y squared times y prime. In other words, you differentiate this the same way you would differentiate it if it was x cubed, but then you need to multiply by y prime. On the right-hand side, the 6 will pop out. And I need to differentiate x times y. So I'll copy my left-hand side down. And over here, I'll differentiate this. So I'm going to use my product rule. So I'll differentiate the x, I'll leave the y alone. That's 1 times y plus. Now I leave the x alone and I differentiate y. There's no need for any chain rule there. The derivative of y is just y primed. So that gives me this. So again, here I'm using the product rule. Now I have an algebraic equation that I can try to solve for y prime. I've got a y primed here and a y primed here. First, let me just distribute that 6 back. So this is going to be 6y plus 6x y primed if I want to get y primed on its own, I need to pull both of these terms to the same side. So I'll take this guy and send him over here. I'll take the 6xy prime from the right and send him to the left. So on the x times y piece here, I have to use the product rule because it's a product, right? Because this is like x times sine x or x times e to the x. I just don't know the formula for y, that's all. So I think of it as x times y, where y I can imagine has some formula, I just don't know it. So x times y is x times that formula, so that's definitely a product rule thing. I can't get away with using a chain rule there because it's not a composite function. Does that make sense?
Yeah, I think I was just thinking, why use chain rule? But no, just
Oh, I
look
got
at
you.
the equation as a whole individually.
Yeah.
Okay.
Yeah, that's the idea. So I think of each side as its own thing. I'm differentiating on the left and I deal with all that shit over here. And I'm differentiating on the right, I deal with all that shit over here. And then only once I've done all the differentiation do I start worrying about how the two sides interact. So I'll leave this piece here. I'll subtract this piece over, and that'll get all my y primes on one side. I'll subtract this piece over here, so I don't have anything that doesn't have y prime. So just like when you were learning how to find function inverses, you want to solve for one variable or another, pull every term that has the variable you want to one side and everything that doesn't have the variable you want to the other side. So I'm going to pull everything that has a y primed to the left and shove everything that doesn't have a y primed to the right. So I'm going to subtract this over, and I'm going to subtract this over. The result is going to be 3y squared y primed minus 6x y primed equals 6y minus 3x squared. So I take all the y prime stuff to the left and everything that doesn't have a y prime to the right. I do that because I want to factor y prime out on the left. If I factor y prime on the left here, I get 3y squared minus 6x times y prime equals 6y minus 3x squared. And now I can divide over by this piece to get y prime equals 6y minus 3x squared over 3y squared minus 6y. Sorry, 6x. 6x. Sorry. So I'm just dividing both sides by this piece. And that's it. That's y prime. Now what I wanted to do is find the equation of a tangent line. So I need to plug in the x and y values at the point where I'm trying to find the tangent. That's 3, 3. So I'm going to plug in 3 for both x and y in the formula I have here for y primed. So the slope of my tangent line is y primed evaluated at the point 3, 3, which is 6 times 3 minus 3 times 3 squared over 3 times 3 squared minus 6 times 3. And there's a lot of symmetry in that equation. You can probably see that. Six times 3 is 18. 3 times 3 squared is 27. So this is 18 minus 27 over 3 times 3 squared is 27 minus 6 times 3 is 18. So even without computing this, I can tell you it's -1 because the top is the negative of the bottom, but 18 minus 27, what is that? -9? 7, 8, 9? Yeah. So this is -9 over +9, which is -1. And then I can give the equation of the tangent line. In point slope form, that's y minus 3 equals -1 times x minus 3. And we can verify. There it is. And just like we thought, the slope is -1. You see here that it just barely kisses the graph. And we could do this at any point, even though this thing is not a function. And that's the work. So the important thing to get comfy with here, the idea of finding a slope and plugging it into the point slope formula shouldn't be anything new. The new stuff, of course, is the differentiation technique of implicit differentiation. So any questions about how we're doing this calculation?
So you're pretty much just singling out y primed, like it's a constant, and then solving for the constant.
Once I get to this stage here, once I get to this stage, I'm just solving for y prime. Yeah, like it's a variable or a constant that you want to solve for in an equation. So the new stuff is really this, right? This is the stuff that we're learning here. Is how to do that differentiation. Any questions on any of those steps? So yeah, what you said was correct. Yes, yeah, we're solving for y prime. Any questions on how we got the equation in which we solve for y prime? Everybody feels comfy?
Yeah.
Okay, sweet.
Sure, I already know the answer to this, but the chain rule and everything needs to be committed to memory.
Yeah, oh yeah. Yeah, you gotta know all the differentiation rules, chain rule included. Chain rule probably the most important of all the differentiation rules. So the next thing I would like to do is to cook up the derivative of some inverse trig functions. In order to do that, of course, I need to remind you what the hell an inverse trig function is, because I know many trig classes are a little bit weak on this. So this is the last big thing we're going to do this week. It's still in section 3.5, but it deserves its own little mention. So first, remember what these things mean, like sine inverse of x is AKA arcsine of x. It's defined by the rule I like the inverse notation like this. So I say that y equals the inverse sine of x if and only if the sine of y equals x and negative pi over 2 is less than or equal to y is less than or equal to positive pi over 2. So if you took trig with me, I know I beat on this stuff pretty hard, but not everybody does. Either way, I know it's possible to forget. So remember that all the inverse trig functions are defined through a similar rule. But so this part, if you replace sine with tangent or cosine or secant, looks the same, but then each one has their own kind of restrictions here. Let's take a look. So I want to find the derivative of the inverse trig functions, which means I want to take this relationship right here, y equals sine inverse x, and hopefully differentiate on both sides and get y prime. The challenge, of course, is this is not a power, right? The inverse notation here means functional inverse, so I can't use like a chain rule thing. That shit will not work. But this is an if and only if. So the rule that defines this function is the same as this. So I can differentiate this implicitly and try to solve for y prime. So I want to find y prime in y equals sine inverse x, but don't have any tools to differentiate directly. That's the challenge. So instead, I'll differentiate this implicitly. With respect to x. So I apply d dx to both sides. D dx of x is just 1. D dx of sine y, the derivative of the outer function there, this is a chain rule thing. The derivative of the outer function is cosine, so I differentiate the outside, leaving the inside alone. And then I multiply by the derivative of the inside. The inside is just y, so the derivative of the inside is just y prime, which means y primed is 1 over cos y. That's all well and good, but remember my goal is to have a formula for the derivative of the inverse sine of x, and to say, well, the derivative of the inverse sine of x is 1 over the cosine of y. Not very helpful. In other words, I want to express this in terms of x. So can I express that denominator, cos y, as a function of x? The answer is yes, of course. But how? Well, I come back to this. Remember that for any variable theta, I'll say it like this, sine squared y plus cos squared y, that's always 1. Which means cos squared y is the same as 1 minus sine squared y. Which means that cos y is 1 minus sine squared y under the square root. But sine y is x. So sine squared y is x squared. So cos y is the square root of 1 minus x squared, because x is sine y. Remember, that's the definition of the inverse trig function. Therefore, my derivative, so say therefore, if y equals sine inverse of x, then y primed is equal to 1 over cos y, which is equal to 1 over 1 minus x squared under a square root. In other words, and here's the thing you really need to remember, in other words, d dx of sine inverse of x is 1 over the square root of 1 minus x squared. So this is how you find the derivative of the inverse sine function. You rewrite y equals inverse sine x as sine y equals x, and then differentiate implicitly on both sides. And then you use the trig identity, sine squared plus cos squared equals 1, to rewrite 1 over cos y as 1 over the square root of 1 minus x squared. You will probably want to go back through this argument. It's a little bit complicated, but it's perfect for your level. It is perfect for a Calc 1 level problem. It's a little bit challenging, but it's all shit that you know. And the output is very useful. This technique can be extended to get not just derivatives of other inverse trig functions, but it's a great way to get derivatives of functions that are in general defined as the inverse of some other function. I'm thinking of logarithms, which are defined to be the inverse of the exponential, at least for us. The inverse cosine function, not super exciting to go through. It's very much the same. I'll just show you here. So a similar argument yields, and just like you need to memorize the derivatives of the trig functions, you need to memorize the derivatives of the inverse trig functions. So this guy, you got to know. And a similar argument will show that the derivative of the inverse cosine function, that is the derivative of arc cosine, if you prefer the arc notation, is the negative of this. So not exciting, not worth going through on its own, at least not in class time, but really good practice for you would be to cook this up. It's the exact same thing we just did, only instead of starting with the definition of the inverse sine function, you start with the definition of the inverse cosine function. And in case it feels like you haven't had enough practice with that to do it on your own, I'm going to do the tangent function for you, because the other super duper important inverse trig function that we play with is arctan, or the inverse tangent function. So now that we have these two, let's go for tangent. So prove this on your own.
Excuse me, sir.
Yes.
Yeah, we know that in pre-calculus, it says when we talk about the cosine of s, that means it is x, and then sine is y, I think so.
So don't confuse the definitions on the unit circle with what we're doing here. It's true that on the unit circle, the x coordinate of a given point is cosine and the y coordinate of that point is sine. Here, we're not thinking like that at all. Here, x is just a variable, and I'm thinking of the graphs of sine and cosine as waves. So there's no connection here to the geometry of the unit circle. Well, I mean, there is, but it's not quite like that. So here, think of x as just a variable, no direct connection to the unit circle.
Okay.
Good point. You do. But yeah, here I'm just thinking of the wave. I'm not thinking of the circle.
All right. Thank you.
Yes, yes. So let's go for ddx of the inverse tangent function next. And this will be the last thing that we do today, besides maybe some examples if we have time. So the definition of the inverse tangent function, y is equal to the inverse tangent of x, means that the tangent of y is equal to x and negative pi over 2 is less than y is less than pi over 2. Very similar to the inverse sine function, only now we have strong inequalities instead of weak ones. This should be familiar from your trig class. And just like we did before, I cannot differentiate this directly because I have no tools that allow me to do so, but I can differentiate this implicitly. So I apply the operator ddx to both sides of tan y equals x. That gives me ddx tan y equals ddx of x. The derivative of x is still just 1. The derivative over here requires the chain rule. I differentiate the outer function, leaving the inner alone, and then I'll multiply by the derivative of the inner. The derivative of tangent is secant squared. So I get secant squared of y times y prime, which means y prime is 1 over secant squared y. And just like I could use the trig identity sine squared plus cos squared equals 1 to clean this guy up, or to clean the last guy up, I can use the equivalent Pythagorean identity for tangent, which is tan squared plus 1 equals secant squared. To then go ahead and rewrite y prime as 1 over secant squared, that's tan squared plus 1, or 1 plus tan squared y. But tan squared y, that's x squared, because tangent y is x. So this is the same as saying y prime equals 1 over 1 plus x squared. And this is because x is tan y, or tan y is x. So summarizing, sorry, here, let me leave this there. I don't want to clutter things. In other words, ddx of the inverse tangent of x is 1 over 1 plus x squared. All right. So we have here the derivatives of our 3 main inverse trig functions: inverse sine, inverse cosine, and inverse tangent. You need to remember these, and you need to get comfortable using them. One of the problems we're going to talk about solving a lot at the end of the term is the backwards derivative problem, where I give you a function, I ask you who has this as its derivative. Rather than asking you to calculate derivatives, I ask you to calculate underivatives or anti-derivatives. And these 3 are good sources of problems like that. So somewhere in your notes, you have the derivatives of the 6 trig functions, sine, cosine, secant, tangent, cosecant, cotangent. Somewhere in your notes, you need to include these as well. And you need to remember them. They're very important. I'd like to do 1 or 2 examples involving the chain rule and the inverse tangent function or inverse sine function. There's a few here, so let's do it. Before I do that, any questions on what we just did or these 3 formulas? Okay. So, where do I have good clean paper? Let's go with this first. Find the derivative. So this is going to be an example involving some inverse trig. F primed of x, where f of x is, excuse me, x times the inverse tangent of the square root of x. So here I have a product, x times arctan root x. I also have an inverse trig function, the inverse tangent. And within the inverse tangent, I don't just have x, I have the square root of x. So there's also some chain rule shit going on there. So this involves 3 different things here: the product rule, the chain rule, and the derivative of the inverse tangent function. First, I use my product rule. So my goal is to find the derivative of this, or this whole thing primed. And I see that that thing is kind of fundamentally a product. It's x times some other function. Oop, x times the inverse tangent of root x, sorry. So my product rule says, differentiate the x, leave the inverse tangent of the square root of x alone, then add that to what you get by leaving x alone and differentiating the inverse tangent of the square root of x. So there's my kind of schematic. It's my plan. X primed, the derivative of x is just 1. So this is 1 times arctan, or inverse tangent, of square root of x, plus x times, and then I need to figure out what this is. It's definitely a chain rule thing. Remember the derivative of the inverse tangent function. Where do I put that? Here. The derivative of arctan on its own is 1 over 1 plus x squared. So here I'm going to differentiate the outer, leaving the inner alone. That's my first step. So that means I'm going to have 1 over 1 plus, not x squared, because my inner is not x anymore, it's square root of x. So this is going to be square root of x squared times the derivative of the inner. So I need to multiply, this is the chain rule, by the derivative of the square root of x. Everybody with me so far?
The second half of that equation after the plus sign, you're using the chain rule to get that answer.
Yep. Yeah, so I'm differentiating here the outer. That's the inverse tangent, and the derivative of the inverse tangent is 1 over 1 plus whatever's inside of him squared, right? So here's the derivative of arctan, 1 over 1 plus whatever's inside him squared. but then I multiply by the derivative of the inside by the chain rule. So then I will continue here. This piece, 1 times inverse tangent root x is just inverse tangent root x plus x times this fraction. Remember, x is the same as x over 1, so I can multiply those straight across. That's x over 1 plus the square root of x all squared is just x. And then I still have here the derivative of root x. That's x to the 1/2 primed. And that last piece I can handle with the power rule now. So this is inverse tangent square root x plus x over 1 plus x times 1/2 x to the negative 1/2. And at this stage, you could call it done, but there is a little bit simplification that can be done here. X to the negative 1/2 is 1 over the square root of x. So this is the same as x over 1 plus x times 2 square roots of x, like that. So remember this piece. That's the same as 1 over 2 square roots of x. So then I just multiply those fractions. And x over root x, these two pieces can interact. X over root x is root x. So this is root x over 1 plus x times 2, like that. This is coming because I can do this algebra here. Okay. So little bits of side work there. And this bottom line, this is as nice as that derivative is going to get. And a problem like this would be a perfectly fair exam 2 straightforward differentiation problem, right? Just like we had a few problems on exam 1, which were just straight find the derivative. I might ask you to straight find the derivative for something like this on exam 2. So we should get comfy with this. There are problems like this and harder on your current homework, and you'll be getting very good at them, but it will require a lot of practice. If you don't practice this shit, it won't happen. Watching the lectures is not enough. Taking notes, even taking really good notes, is not enough. If you Symbolab or Wolfram Alpha your way through the homeworks, that will bite you in the ass big time on the exam. But if you practice this stuff, you'll become a differentiation wizard. You know, you'll feel so confident that you can differentiate anything, and it's a really good feeling. I remember that. I remember this moment in Calc 1, and that sense that yes, I can differentiate fucking anything, because you got the rules now. You can do it.
So my hardest thing is just looking at it and deciding which law or theorem to use. I don't know how you call it, but
no, I dig it. Yeah, which differentiation rule, right? So you look at this here, and it's like, where do I begin?
But it'll happen as we keep going. Just like I have committed all of those other theorems from test 1 to memory, and now it's just like you don't think about it type thing.
Pretty much, yeah. I think of it, it's kind of like an order of operations thing.
Yeah.
So when I look at this, the outermost operation that's going on, aside from the derivative, is this multiplication.
Mm-hmm.
So when I look at this, I fundamentally see a product rule.
Right.
My first line here is expanding that according to the product rule. And once we've done that, we can kind of look at each little piece and ask, okay, well, what do I need for that?
Chain.
Yeah, this guy is straightforward. He's just a power rule thing.
Right.
No work there. But this definitely looks like a chain rule, right? Because I've got the outer function, arctan, and the inner function, root x. So you're exactly right. Yeah, I look at this piece and I see chain rule. So then I use the chain rule on him, and that schematic looks like this.
And that's where it gets confusing, but I like your notes on the side.
Yeah, I'm glad. So let me try to de-obfuscate a little bit, because I think Caleb also wanted to see something from the third line down here. So let me see. I can use this page, right? So if I apply the chain rule in general, you guys remember, like I gave you that general version of derivatives of exponentials the other time, e to the u all primed is e to the u times u primed. Well, what if I wanted to look at a general form of the derivative here? So if I assume that u is a function of x, then the derivative of the inverse tangent of u, I follow my formula, it should be 1 over 1 plus u squared times the derivative of u. And that's really all I've done here. So if you compare the above to the third line here, particularly this piece, I'm leaving the x alone. I'm not doing anything with him, but this stuff right here really is just this. So the derivative of arctan of some shit is 1 over 1 plus that shit squared times the derivative of that shit. 1 over 1 plus that shit squared times the derivative of that shit. And that's exactly what we get here. The shit just happens to be root x. So you get 1 over 1 plus root x squared times the derivative of root x, because that's my inner function. Whatever that is what goes into that formula. And then I break this piece down. So root x is x to the 1/2. So root x primed is x to the 1/2 primed. From here to here, I did a couple little things with this piece. So first, the square root of x all squared, that's just x. So that's this. When I square the square root goes away. And then this x, which originally was out front, I bring him in as the top of the fraction, because x times some stuff is the same as x over 1 times that stuff. So I multiply the top with the top and the bottom with the bottom. X times 1 is just x, so that's multiplying the top of this fraction with the top of this fraction. And the bottom 1 times this denominator is just this denominator. And that denominator simplifies to 1 plus x. Just, again, squaring the square root gives me this. And the rest of it is just algebra. So I differentiate this piece according to the power rule. And then 1/2 x to the negative 1/2, I can write that as 1 over 2 square roots of x. So that's 1 over 2 square roots of x times x over 1 plus x. Again, fractions multiplying, so I multiply the tops with the tops and the bottom with the bottom. So if I multiply x times this numerator, that's x times 1, so that just stays x. And then I multiply this denominator with this denominator, and I get 1 plus x times 2 times root x. And then my very last step, upstairs here I have x to the 1, downstairs here I have x to the 1/2. 1 minus 1/2 is 1/2. So the x over root x piece simplifies to root x. So each one of these steps is tractable, but it's a lot of algebra and a fair bit of calculus here in this problem. So Caleb, did that resolve your question about the third line?
Yeah, I did. Thank you. There was just a lot of noise earlier, so I didn't want to turn on my mic.
No worries. Anybody else have any questions about any one of these steps, or where things are coming from, where they're going, why we're doing it?
I have a question.
Yeah, go ahead.
So in your last final result, you had x over the square root of x. You did 1 minus 1/2. Why isn't it 1/2 minus 1? It would have changed it, you know?
That does change things, yeah. So remember, a to the x over a to the y, that's the same as a to the x minus y. So I'm using this rule for exponents here to simplify that fraction. Does that look familiar? This rule for powers? Like x cubed over x squared is the same as x to the 3 minus 2.
Okay, it's been forever.
That's okay. Yeah, so Calc 1 basically makes sure that you remember every little bit of your algebra. That's what I'm doing, and I'm doing it just with, I think I have some other colors here. I'm doing it just with this piece. Oh shit, that's black too. I'm doing it just with this piece. So the x over root x piece simplifies to root x over 1. So the purple circled piece there simplifies to the purple circled piece here, according to these rules.
Okay, thanks.
Yeah, of course. What else are we thinking? I know this is a windy and wandering problem. There's got to be other questions. What else are we thinking?
On the second to last line,
Yes.
the denominator comes from you multiplying it by the fraction that you got in the top right corner there, right?
Yes. Yep. So on this line, this denominator is this denominator, 1 plus x, times this denominator. So this guy is the same as 1 over 2 square roots of x. So when I multiply those fractions together, the denominator will be this denominator times the denominator here, which is 2 root x. So I have 1 plus x, the denominator from the first fraction, times 2 root x, the denominator from the second fraction. If you wanted to be a little bit more verbose about it, we could say x over 1 plus x times 1 over 2 square roots of x, right? You could insert that as a line here. And that's the same as x over 1 plus x times 2 root x. And that's what we got.
Thank you.
Of course. Anything else on our minds when we look at this? Okay, if you go to the bottom of page 214 in your textbook, they do list the derivatives of all 6 inverse trig functions. The 3 that I require you to know cold are the inverse sine, inverse cosine, and inverse tangent derivatives. So make sure that you have those in your notes. If not, just go back. I displayed them all on the screen at one time for a second. Last little thing before I let you go. We don't know how to do this yet. The derivative of the natural log, we don't know yet. But I do know that y equals ln x means the same thing as e to the y equals x. So the same trick that we use to get the derivatives of the inverse trig functions can be used here. And if I differentiate implicitly on both sides, the derivative of e to the y is e to the y times y prime. The derivative of x is 1, which tells me that y prime is 1 over e to the y, which is the same as 1 over x. So the derivative of ln x is 1 over x. And this is a really big deal. I'm going to go back through this again on Monday of next week. This isn't in your homework, so don't panic about it. But because it's the same skill that we're using right now, I wanted to show you really quickly. Next week, we're going to start talking about logarithmic differentiation, and then we're going to start looking at some application problems. We're going to start seeing how to solve related rates problems, problems from the real world involving physics, which are hugely important. Really the main thing in Calc 1 is going to be solving optimization and related rates problems using all the shit that we've been doing. So I implore you, over this weekend, please work very hard on this homework. I will be working very hard grading your tests. I'll ask you to work very hard on this homework. And when we meet on Monday, you are all going to be master differentiators. And then we will take those skills and start applying them. So next week begins what for many is the hardest part of the course. Right? I guess that's what I'm trying to say here is the application stuff, you need to be really, really good at the calculations in order to have a chance at wrapping your head all the way around the applications. I'm going to try to start gentle, but just be aware that it's a difficult part of the class. So please work extra hard. Make sure you're caught up on Monday. Work really, really hard on homework 6. If you have older homeworks that need to be open so you can go back and finish them before 6, that's okay. I will be taking a look at the WebAssign extension requests after my office hour today. So if you need anything popped open, please go ahead and submit a request now. Homework 6 is open. It's been open since Wednesday afternoon. Please get in there and work on that. And I would love it if everybody feels like rock star differentiators by Monday. If there's anything you feel that is between you and that, reach out to me and I'd be happy to work with you either with an extra office hour or just through email, whatever you like. Any last minute questions before we sign out for the day? All right, then that's where I'm going to end the lecture for the day. Hope you guys have a lovely rest of your morning. Please do work hard on that homework. And if you need help with anything, don't hesitate to ask. Remember, I'm here, or if you need like immediate direct help, follow the link to tutoring. So go to our Canvas page. I've got a link that says, you know, you can reach our tutors here. They're pretty good, especially when it comes to this stuff. I can specifically recommend Alejandro. He's a badass. He works in the Learning Commons. He's also with me on the math team. He's a great guy and he really knows his math. But anybody that they have over there would be happy to help you with these derivatives. Please work hard. And if you would like help with anything, ask for help. And then I will see you either in office hours or on Monday. All right, take care, guys.
Good weekend.